Assalamualaikum and good day for Puan Nur Azrina, which is my lecturer for this course is Mathematics Engineering 2, Section 5, and all Bureau classmates. We are from Group 5 and Section 5. We will present our project, which is Project 2. Before I continue the presentation, I will intro my name and my group name. My name is Fatuda binti Zaidi. We have 8 group members. This is Muhammad Fahim bin Muhammad Hisham, and another name Muhammad Farihin bin Muhammad Faizal, Muhammad Mubarak bin Abdul Jalil, and next is Muhammad Nur Akmal bin Zuhaini, and Nur Aziatul Syuhada binti Muhammad Faizam, and Nurul Najha binti Jaafar, and last but not least is Tan Ying Sing.
So now, let's start with example 3.10. The general equation describing the mass spring system is m d square x over dt square plus b dx over dx plus kx equal to f. A spring is strength 0.3 meter equal to delta L when 5 kg of iron ball is attached. The weight is then pulled down an additional 0.2 meter and released with an upward velocity of 2.5 meter per second. Find an equation for the position of the spring when it is under undamped free vibration. Now, we begin with the general second order differential equation for a mass spring system with damping and external force. M d square x over dt square plus b dx over dt plus kx equal to ft. In our case, there is no damping and no external force, so we remove b and ft. Next, we calculate the spring constant using the formula k is equal to w over delta L, where w is the weight and delta L is the strength caused by the weight. So, k is equal to w over delta L equal to 5 times 9.8 divided by 0.3 equal to 49 over 0.3. Next, we substitute the value of mass m equal to 5 and the spring constant into the undamped equation. So, m d square x over dt square plus kx equal to 0 will be 5 d square x over dt square plus 49 over 0.3x equal to 0. To simplify, we divide the entire equation by 5. So, d square x over dt square plus 49 over 0.3 times 5x equal to 0. So, d square x over dt square plus 98 over 3x equal to 0. This is a standard second order linear differential equation with no damping. The general solution is of the form xt equal to a cos omega t plus b sin omega t. To find omega, we use the formula omega equal to square root k over m. So omega is equal to square root 49 over 0.3 divided by 5. So it equal to square root 163.33 over 5. So the omega will be equal to 5.715 radian per second. Now we differentiate the position function to get the velocity function. Vt is equal to dx over dt is equal to negative a omega sin omega t plus b omega cos omega t. From the problem, we know the object is pulled down 0.2 meter. So x0 is equal to negative 0.2. So now let's substitute this into the xt. X0 equal to a cos 0 plus b sin 0 equal to a. So a is equal to negative 0.2. It also says that the object is released upward with the velocity 2.5 meter per second. So v0 is equal to 2.5. Now substitute into the v2. So v0 is equal to negative a omega sin 0 plus b omega cos 0 equal to b omega. So b is equal to 2.5 over w equal to 2.5 over 5.715 equal to 0.438. So finally, we substitute the value of a and b into a general solution to get the complete motion equation. Xt is equal to negative 0.2 cos 5.715t plus 0.438 sin 5.715t. This is the equation for the position of the mass over time during undamped free vibration.
I will explain the example for 3.11, which is about second order differential equation in a mass spring system under indamped free vibration. In this example, an iron ball a weight 98 Newton is hanging from a spring. The spring straight 1.09 meters, which is the essential length. So the question from this, we want to solve how much cycle per minute the system will extrude, and the equation of motion is the ball is put down 0.60 meters and released from rest. First, we find the spring constant. So the spring constant is 89.91 Newton per minute. And after that, we find the mass, which is 10 kilogram. We calculate the angular frequency, which is omega. The omega is 3 radian per second. We convert to circle per minute, which is the frequency is 29 circle per minute. After that, we find the equation of motion. The equation of motion is yt equals to a cos omega t plus b sin omega t. When y0 equal to 0.60, we put the 0.60 into the y. So the value of x is 0. So we calculate and we get a equal to 0.60. Based on this equation, the velocity is 0. So the value of b is 0. So the final answer is the motion yt equal to 0.60 cos 3t.
For the last question, a spring is stretched 0.25 meter when a 4 kilogram block is attached to it. The block is then pulled down an additional 0.15 meter and released with an initial upward velocity of 2 meter per second. Assume the system undergoes undamped free vibration. So find the equation of motion for the block displacement from its equilibrium position as a function of time. Now, we start by calculating the weight of the block using the formula W is equal to mg, where mass is 4 kg and the gravity is 9.81 meter per second square. So W is equal to mg equal to 4 times 9.81. So it will be equal to 39.24 Newton. Next, we calculate the spring constant using K equal to W over delta L. So it will be 39.24 divided by 0.25. So the K is equal to 156.96 Newton. Now, to find the angular frequency omega, we use the formula omega equal to square root K over m, where m is the mass for kg. So omega is equal to square root 156.96 divided by 4. So equal to square root 39.24. Next, this is an undamped free vibration system. So the general solution is xt equal to a cos times square root 39.24t plus b sin square root 39.24t. So the block is pulled down 0.15 meter from the equilibrium at t is equal to 0. So x0 is equal to 0.15. So a is equal to 0.15. Now we differentiate xt to get the velocity function. So will be negative a omega sin omega t plus b omega cos omega t. So it is released with an initial upward velocity of 2 meter per second. So it will be at t equal to 0. X prime 0 equal to negative 2. So negative b omega equal to negative 2. And b omega equal to 2. And v equal to 2 over square root 39.25 equal to 0.319. So finally, we substitute the value of a and b into the general solution. So xt is equal to 0.15 cos square root 39.24t minus 0.319 sin square root 39.24t. So this equation represents the displacement of the block from its equilibrium position as a function of time.